answer there? No answer?
It says first argument of solve or C solve must be an equation or an equality.
Huh? No answer, huh?
No, my PI is not long enough to put all it.
Put all of it, huh?
17.
Oh, okay. Yeah, I made the shift more. 40 miles an hour?
Like 39.1.
So, okay, finally, no ticket. So you see that it could work generally. You can even have cars flowing by. The police can have it open, and then you could be at random angles, and the instrument can still show you the velocity output of that car. And then the last topic is the sonic boom. This interesting shows you, the program shows you what happens when you break the sound barrier. You see? So each time you're creating a wave, you're going just as fast as the wave. So none of the waves are in front of you. You see? So you kind of create a wall in front. It's like a wall, a barrier. So it says here, now the source is moving at the speed of sound in the medium. The wave fronts in front of the source are now all bunched up at the same point. You see? As a result, an observer in front, so if there was an observer here, so if there was an observer in front of the source right here, imagine this, the observer was like right here. He wouldn't hear anything until the source went by him. So nothing is observed, nothing is heard in front of the source. See? And then the source goes by, then he can hear it. So it says F is C plus 0 over C minus 0 is infinity. An observer behind the source will hear a lower frequency. So here this is B plus B. So if a person is here, he's going to hear half the frequency. You see? V minus Z, 0 over V plus V, 0.5. So you see the waves are twice as much as what they should be. So the frequency is half as much. But in front, the frequency is infinity. It means if you're in the front, you never hear anything. Right? It takes infinite amount of time for the wave to come to you. So now this one is a simulation that you're going 1.4 the speed of sound. See, so you create a cone like this, It says, since the source is moving faster than the sound waves it creates, it actually leads the advancing wavefront. You see the difference? The source is going faster, so it leads the wavefront that is created. So it creates a cone like that. The sound source will pass by a stationary observer before the observer hears the sound. So you mean if it was here, if I was like here, the source would move past me, and then I would hear it. This is kind of weird, huh? Here, I would hear it exactly when the source reaches me. Here, it would be something like boom, 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 you know. I hear it after the source passes me. So as a result, an observer in front of the source will detect V plus 0 over V minus 1.4, negative 2.5 F0. And that means, well, that just means it's weird. Like, what does it mean to be negative? It's just you're hearing it after the fact, you see. An observer behind the source will hear a lower frequency, V minus 0 over V plus 1.4. So 0.4. So that one is interesting, you see. Here, if you're behind, it's less than half. Okay? Because the wavelengths is even larger here than here, you see. Here the wavelengths are twice as much as they should be. So it's one half. Here it's more than twice as much. So it's less than half. You see? So it's a pretty good program that they do to simulate this. So then there's an equation that they make for the apex angle of that cone. So imagine this is the cone that's created. And imagine this is the airplane or rocket. So this is the angle theta. Right? So then you can say here, when this wave was created, the airplane was in the middle of that wave, right? So it's like something like this. Imagine, take one of these circles, say the plane was over here, right? When this wave was created. Then, by the time that this wave spread out this distance, now the airplane is here, right? So then the cone that it makes, is tangential to that circle, right? It's tangential to that circle, so this is 90 degrees. So then what's the angle? What's the angle of that? So then it's going to be the distance that the airplane went is velocity of the airplane, we're calling it velocity of the source, right? Velocity of source times time. And then this distance is velocity of sound times time, right? Velocity of sound times time. So the angle of that is going to be sine of theta is going to be V sound T over V source T. T cancel. So then that's going to be the angle. So in the case of that one, they were showing what? V of the source was 1.4 V sound. So sine of theta would be V sound over 1.4 V sound. So that one cancels 1 over 1.4. Okay, and then that's going to be .6 degrees. So that should be the angle of that cone, you see? I don't think I could pause it. I wish I could pause this. If I clicked on it, no? If we measure that cone, it should be 45 degrees. Screenshot it, huh? on a moving. Oh,
Yeah, that worked.
it worked. See,
Make it big.
everything is doable, guys. Everything, even getting an A on Wednesday's layout.
We'll see.
Now put a protractor there. Anyone have a protractor?
No. Yeah.
You don't walk around with a protractor in your hands? Oh my God, what happened to this generation?
I lost mine. Right here. Oof.
That's about 45. I think, yeah, we need to measure from the center of the source, right? From the center of the source. Yeah, 45. So if your simulation is correct, it should abide by the rule. Good job, it worked out. Okay. This also happens in the boats. When it happens to a boat, it's called a bow wave, right? We don't talk about those a lot, but they should give you a bigger picture here. Those waves are created by the bow wave of a ship. So if a ship is going in water faster than the speed of the waves in water, it will create a bow wave like this. I mean, these dolphins are managing those waves, right? They're having fun. They're surfing the bow waves. Let's see what other good ones are there.
Oh, I see. Cool.
It's not that good of a video because it's not showing what's creating. Okay, so it's created blue Pacific Ocean ship bow wave. But it didn't actually show that. It would be nice if it showed the actual.
Away from boat.
Let's see if this shows. Yeah, see the ship is at, I think the reason why they're not showing it is oftentimes the person taking the video is in the ship. Right, that's why we're not seeing the ship itself. So they're taking a video as the ship is going like this, and then they're showing the wave this way, right? Well, this is cosmic bow waves.
Cosmic bow shocks. Presented by Science at NASA. Imagine an object moving at supersonic speed. This object, as it moves through a medium, causes the material in the medium to pile up, compress, and heat up. The result is a type of shock wave, known as a bow shock. A bow shock gets its name from bow waves,
That's
the
what I wanted
curved
to
ridge
show.
of water in front of a fast-moving boat created by the force of the bow pushing forward through the water. Bow waves and bow shocks can look similar. However, bow waves only occur on the surface of water, while bow shocks occur in 3 dimensions. There are bow shocks everywhere, even in space, and these cosmic bow shocks can tell scientists cosmic secrets. Even the emptiest regions of space contain protons, electrons, atoms, molecules, and other matter. When planets, stars, and the plasma clouds ejected from supernova fly at a high speed through this surrounding medium, cosmic bow shocks are generated in that medium. The solar wind forms a bow shock in front of Earth's magnetosphere. The fast-moving plasma of the solar wind blows past Earth, but it cannot penetrate our magnetosphere, explains Maxim Markovich of NASA's Goddard Space Flight Center. The solar wind has a magnetic field, and the Earth's magnetosphere is almost like a solid body for that wind, so the solar wind forms a bow shock in front of the outer edge of the magnetosphere. Studying Earth's bow shock can unlock the secrets of the solar wind, allowing us to better understand its complicated effects on our planet. The high-speed collisions of stars with the interstellar medium create impressive bow shocks. Hot supergiant star Kappa Cassiopeia creates a shock that can be seen by the infrared detectors on NASA's Spitzer Space Telescope. In this Spitzer image, the pileup of heated material around Kappa Cassiopeia is indicated in red. Studying stellar bow shocks can reveal the secret motions of the underlying stars, telling us how fast they're moving, which way, and what they're moving through. An example of a bow shock on an even grander scale is seen in this cluster of galaxies located in the Carina constellation, called 1E 0657558. This X-ray image from the Chandra Observatory captures the moment of a gigantic collision of 2 smaller clusters, the 2 white regions in the image. Markovich says, the clusters are filled with hot plasma, and one of them, the cluster on the right, is smaller and denser. As it flies through the less dense cloud of plasma that is the bigger cluster, it forms a bow shock. Scientists study such cluster shocks to deduce their velocity in the plane of the sky. The fine structure of the shocks reveals a lot about the interesting, complicated physical processes in the plasmas present in clusters, as well as many other astrophysical objects across the universe. For more on shocking phenomena found beyond our solar system, stay tuned to science.nasa.gov.
I like the way you did a pun at the end. Shocking phenomena. Okay, now let's start a little bit into chapter 18.